All right, this is page 3. Should go pretty quick. It's only 3 questions. Diagram below shows 2 negatively charged balloons suspended from non-conducting strings. Very interesting picture. What occurs as the student brings the balloons closer to each other without allowing them to touch? Well, they're both negative, so they're going to repel each other. And as the R gets smaller, remember Fe K Q1 Q2 over R squared. So it's an inverse relationship. So as R goes down, the force goes up. So all your questions are talking about the force. The force between the balloons increases, and they repel each other. So the answer is C. Question 16, which graph best represents the relationship between the electric field and the distance R from the point charge? So think about this. If you have a point charge, okay, let's say it's positive. Doesn't matter if it's positive or negative at this point. If you put another charge here, a positive charge, it's going to feel a force, right? It's going to be repulsion. It'll be K Q1 Q2 over R squared. If I want to know how strong the field is at that location right there, the field is just equal to the force divided by the charge. So it really doesn't matter what the size of the charge is that you put there. It divides out. So your field strength is actually KQ over R squared for a point charge. We did this similarly with gravity. If you remember, we said Fg was equal to Fg. So Mg equals big G M1 M2 over R squared. And we divided an M out, and we got the gravitational field strength was Gm over R squared, where this was like, say, the mass of the Earth, and this would be your distance away from the center of the Earth. So very similar. This is this charge. R is your distance away from that, so that'll tell you the field strength. So what does this graph look like if it's E on the y-axis and R on the x? It's an inverse square relationship. Just means it gets weaker as you go away from the charge. Last question on this page. The diagram below represents a source of potential difference connected to 2 large parallel metal plates. The key here is this is our sort of uniform parallel plate, right? The field is uniform between them. So which statement best describes the electric field strength between the plates? Well, the word uniform means constant. So I believe the answer is it's the same at A, B, and C. All right, I'm going to try and squeeze in the 4th page here, number 18, in one video. So here we go. Moving electron is deflected. So key here is it's an electron, right? It's deflected as it moves between 2 positively charged plates. If it deflects upward, that tells me that this plate has to be positive because that negative electron is attracted to it. So that means this has to be negative because they're oppositely charged plates. Now, the trick here is you think the electric field points that way because you're watching this arrow showing the electron deflected. But if you remember, the E field is based on a positive test charge. So if we put a positive in here, where would the field point? The field would point in this direction, right? That's what a proton would have done. The field doesn't change. We have to agree on this. The fact that it's an oppositely charged electron, it does the opposite of what the field says. So the answer would be whatever from C to D. I think that's D. Okay. Next question. Diagram below. 2 identical spheres, A and B, have equal net positive charges. Which arrow best represents the direction of the resultant electric field at point P? So the electric field, again, positive test charge. If I put a positive there, the positive at B would repel it. The positive at A would repel it. And if you want to know what the resultant of those 2 fields are, resultant just means add them. So the way we add vectors is we put them tip to tail. So the net is going to be that, which is A. The other way to think of it is if I break this into components, this X component and this X component will cancel each other out, and I'll be left with 2 upward Y components, which is still that answer. Which diagram best represents the electric field around a negatively charged sphere? Well, first of all, let's get rid of all the curved ones. I don't know why curves make you guys happy. Don't do that. If it's negative, remember, we put a positive test charge out here. Would it be attracted or repelled? It would be attracted, so this is wrong. The answer is B. Next question, electrostatic force. So we have Fe is 20 newtons, is exerted on a charge. Q is equal to 8 times 10 to the negative 2. What's the magnitude of the electric field? The formula is Fe over Q. This is one of those easy questions. Just divide the two, and the answer is B. 22, what's the magnitude of the electrostatic force? They want to know Fe on an electron, right? The electron, can't see this 1, 2, an electron, that means Q is that 1.6 number. So we know Q. We want to know what Fe is, and they tell you the electric field. Again, you're just going to use this equation and say QE is equal to Fe. Just remember it's an electron, so you use the 1.6. They're asking about the magnitude, which means you don't have to put the negative in there. We really never do. We just use common sense. So the answer for that would be A. 23, how much work is done in moving? So you want to know work. You have 5 coulombs of charge. That's Q. And the potential difference, V, is 12 volts. This is what we have to do a better job of when we read, pulling out the information and writing it down. When you do that, it makes it pretty easy when it's just following a formula. We have voltage or potential difference. We have the charge. All right, so all we have to do is find W. It's Q times V. So it would be 60 joules, which is answer D. Last question, the energy required. So again, remember, we talked about W being work, being energy, being potential energy, being kinetic energy. All those kind of fall under the W symbol to move one elementary charge through a potential difference of 5 volts. This would be real easy, if I wrote this out, work is equal to QV. If we left it in elementary charges, it would be 1 elementary charge times 5 volts would be 5 EVs. Unfortunately, none of our units are EVs. So I can't just put in 1 elementary charge. I have to put in the 1.6 number. And that will give me an answer in joules. And I think it's 8 times 10 to the minus 19, which is answer A.